Hey everybody, this is Larry. This is the last day of the August Leetcode Day Challenge. Yay, congratulations everybody. Yeah, let me know what you think. Hit the like button, hit the subscribe button, join the Discord, and let's look at today's problem. Hopefully it's a fun one. Delete node in BST. Given a root node and a key, delete the node of the given key, return the root node reference updated. Okay. Yeah, because you have to search it. That's fine. I think keep on beeping. Okay, so I mean there are a couple. So this seems pretty straightforward conceptually, in that it is, the search part is easy. You just have to search, and then if it's found, deleted, right? And this is a very textbook problem, so in theory you know how to handle this, and if not, you can read up a book. For me, I actually don't remember exactly how to delete it. I mean, I know how to delete it, but I don't remember I know all the rules. So let's say, so I think for me it's just about going for the cases. So let's say we delete 3, right? In this case, we delete 3. Do we promote the left or the right? In this case, it doesn't really matter. But let's say 4 has, maybe another example is, okay, we delete 5, right? Do we promote the 6? What if 6 has something small? Okay, yeah, something like that, right? So yeah, so I think it's just figuring out how to update it, and I think I actually don't remember how the textbook version of how to fix it is, to be honest. The way that I would do it maybe is just the way that I think I would do it, just as a naive thing, would which is also would be O of H, where H is the height of the tree, is just replace whatever key that you found with the node that is the smallest number that's bigger than it, or something like that, right? Would that be good enough? Because the smallest number that is maybe not, because then if you have a linked list situation, that wouldn't work, right? So actually, I would say I probably don't remember exactly how to promote it. Because, for example, in this case, if we remove 5, how do you want to promote it? Right? I mean, I guess you could look at this and be like, okay, let's promote the 6 and then 7, right? But what if you have like just a full tree of, let's see if this shows up. Yep. Let's say you have a tree of something like, let's say this is 6, this is 7, this is 5, this is 8. So now you have a full tree here. Let's say you remove 6. Oops. Let's say you remove 6. How do you can't just promote the 7, because then the 5 would be weird, right? I guess you could promote the 5, or promote the 7, and then just recursively take a random one and promote it. Is that weird? Does it have to be anything? No, because you can't do it that way, because if you promote the 7, then you can't promote the 5, because the 5 has to be to the left, right? So that's a wow, maybe I just don't know how to solve this one, to be honest. Just because I don't remember the specific algorithm. So yeah, so in this case, how do you remove the 6? At least in a non-cheesy way, right? Because we could probably do some crazy things. I mean, in theory, in here, we could replace the 6. Also, this is just wrong, but so actually we want 5. Oops, sorry, friends. But yeah, if you remove this 5, then can you put you put the 7 here, but then the 6 has to be on the left, so that doesn't make any sense. I actually really don't remember. I'm trying to think right now. Sorry for wasting your time. So, if you're new to the show, this channel, I usually do this from live. Many times I already know the answer, or I could solve it very quickly, so I'm able to explain it as I code. But this one, I am a little bit stumped, just because even though it is a very elementary, computer science algorithm class E problem, it's just that like this never comes up, so I guess I don't really remember how to do it. And I have a couple of strategies that I would try to think about how to do, but I don't have, or like I'm not convinced that it'll work all the time. Right? For example, maybe one strategy is okay, replace the 5 with the 4, and then okay. But then now if you have something like 1, 2, 3, 4, oops, like you have a linked list. That's not a linked list, but like you have something like that. What happens if you remove the 2, right? Well, you're not going to, so that's a little bit, I mean, you put up the 3, but I'm not sure that, so there's definitely a couple of things here, and I really don't know what the answer is, to be honest. And I think, so maybe this is a good example for me to go over what I would do when I see a problem that I don't know, and I try to figure out how to learn about this. The first thing I would do is I would just look up the solution, or not the solution, but like the algorithm, right? And what I mean by that is, and when I talk about looking up the algorithm, I don't mean the code. I just mean like someone explain it to in words, right? So okay. So apparently there are multiple cases. Wow. So this is not. So I don't feel as bad. Okay. So I did get it to here, and this is me just reading this. So read it with me. And if you're watching this video, I hope that you get something out of this, because I imagine if you can actually find this problem anyway, because this is a textbook problem, so you can find it in your textbook. But for me, I'm just trying to demonstrate how I would learn a new problem. Okay, so then here, search for node remove. Okay, so we know that. Remove is in detail. Algorithm for lookup. Okay. There are 3 cases. Okay, so node to remove has no children. That's easy. Okay, that's true. Node to remove has 1 child. If there's only 1 child, then that's also trivial. Okay, that makes sense. And then now the 2 children part. Okay, wow. So I guess I did have it. It's just that I didn't think about doing them in 2 cases, or in 3 cases in this case. So okay, so basically I did actually have it. I just wasn't able to. I think what I was trying to do was trying to have 1 case to fit them all, but it turns out that just watching this, reading this, there's just 3 cases, and we just have to handle it. And I already know these 3 cases because we kind of talk about it on the stream, on this cast. And the thing that, so there's some code here which I'm not looking. So the thing that I would do when I look at, and this is true for competitive as well, is when I look at the editorial, I read the editorial, but I rarely read the code, because now that I have the idea, I will force myself to implement as best I can, so that I get practice implementing it, even if I don't know it, right? Or know the algorithm, because then now I can implement it in my own words, and then afterwards, conceptually, depending on how messy it is, I might look up other code to see how other people might implement it. For me, I have about, at this point, to be honest, about 20 years of programming and implementation, so I could probably generally implement anything that's reasonable anyway, but that doesn't mean that I can't learn. It's just that usually that's not the part that tricks. Oh, I could get something done, but it might not be as clean as possible. So okay, so now we just have to go through our things and find the node, right? So okay, so let's have a find function. Key, node key. If node is none, then probably messed up somewhere. But otherwise, if node dot was it value is equal to key, return node. If node dot value is greater than key, then we return find node dot left. Else return find node dot right, right? So those are the three cases. We get the node. We can probably play around with this. Just let's just print the find of root of key so that we can kind of see if these see if these finds the 5 with one-time error. So we do have, oh, I forgot to pass along the key. So I guess I did know, I just didn't remember to put them together that way. So it is able to find the 4 and the 5 in a very O of H kind of way. So now we have the node. So node is equal to this, and then now we can think about three cases, right? If node that's a little bit messy. Well, now I'm just thinking about like, okay, now we found the node, but in order to remove it, we have to we have to remove the node. So you need kind of need the pointer reference, but I guess not really. That's what I was thinking about, right? So now if node dot left is none and node dot right is none, so this has basically this is a leaf. Then we have to set node is equal to none, but that doesn't change the reference to this, right? So so that's what I'm thinking of. So I need the parent to this. So okay, so how do I fix this? So if node is none, just with none doesn't really matter. If code is equal to key, let's just pass in the parent. Yeah, let's just find in the pass in the parent so that we can return the node and the parent. This and node. No, actually, this is good. It's just that we put in the thing on the thing. And this is just none as a parent. Though we might have to change the root reference as a result if we have to remove the root. We will play around with it. But if this is a leaf, then in this case, this returns node parent. Parent dot. Oh, this is a little bit messy as well because you have to choose which you have to show which you have to return which way it went. How do people do this, man? I just talked about how good I am in implementation and then I just can't remember how to do it. Yeah, actually I guess we could just check manually if parent.left is equal to, this is actually not great, but node parent.left equals none. If parent.right is equal to node, parent.right is equal to none, right? Yeah, and if parent is none, then root is equal to none, because that means that the parameter is the root. The root variable, not just the root node itself. Okay, and then now we check else if node.left is not none. That means the well, okay, let's just do both children. It's not none, and node.right is not none. And this is again through like what you saw me with the Googling for maybe 20-30 seconds. That's all I needed to know how to implement this, right? So my memory may be a little bit fuzzy, but that's basically what I'm doing. Okay, but also because I already kind of had an idea of what to do, right? So okay, so that means that we have both child, get the biggest number that is smaller than and this target or key. Do I want to write another function, or is it just annoying? Okay. Yeah, find less than, I guess. Well, what do we want to go? We want to go left, and then we want to go as right as we can, right? Yeah. So actually we could just do a while loop, I think. So current is equal to no dot left, while current dot right is not none. Current is equal to current dot right, and then yeah, and then now current should be the smallest value. So now no dot value is equal to current dot value, but then now we have to get the parent again. So right, parent is equal to the node. Because then now we're removing this number, right? So so we have to remove references to this node. So basically, yeah. So basically that, right? And then now we do the same thing of this thing. So now maybe we can abstract that parent reference, say parent node. Also, I think I use bad casing for it because I think I use the other. I generally use the other one, but I mean this is current. We want to remove current. Okay, and then now if only one child, right, is not none, then no. So then parent dot left. So if there's only one child, then we set the parent to whatever it is. Okay. So if parent dot left is equal to, okay, if parent is none, then root is equal to no dot left. If parent dot, oh, I think this needs an else, just to be sure. Maybe it doesn't, but is equal to node, then parent dot left is equal to node dot left, else parent dot right is equal to node dot right. This is going to be messy to kind of is this right? No, this is node dot left still, but yeah, maybe I could I don't know. This is a mess. I don't know that I expect this to be correct, to be honest. But you know, it's a learning experience. Let's see if it is at least right for these. So this is okay for the second case, but not the first case. I removed the 5, and 5 is what does this tree look like again? Oh yeah, we removed the 5 and we put the 4 here, but then now I feel like, well, I mean, it's okay except for that I'm now missing. Oh no, this is okay. If we have the same amount of numbers, it's just a different tree, right? because there could be multiple trees. Okay, let's do, you know, 1 element, 2 element, and there are a lot more cases, obviously. Ooh, that's good. I don't know which one it's erring on though, but conceptually that's good. None type has. So it doesn't even find this at all. That's odd. Let me double check that this is the one that I'm erring on. No, that's, well, my answer is wrong. I thought this should take care of it for me. Why is the parent not none? That's actually, okay, let me print this out real quick. Yeah, so this is none. So then, yeah, so this should call here. Which, oh, this is, okay. I got it. It's just that I, silly Python, my understanding of Python is fine. It's just that I didn't do it correctly. Okay. So then now, that means one of these other ones are incorrect. Or at least it gives me an error. Line 34. So why is this none? It doesn't find 2? That doesn't seem right. Is my tree set up incorrectly? It may be. Oh yes, that's my bad. Okay. You give it bad input, it'll give you bad input. Bad output, I guess. Garbage in, garbage out. Okay, let's see. Okay, so this looks good. It's just that I misunderstood the thing. I think there are probably a couple more edge cases that I would test. I think the big one being the leaf. So let's do that. Actually, I would already test that. So okay, let's just submit it, and then I'm not 100% confident right now, but yeah, I would. That's why I'm testing this. Oh, did I miss? Oh, because if it's not found. Okay, I didn't. I thought that for some reason that I thought that it has to be in there. So that's fine. That's easy. Because if node is is none. Oops. Then return root, because then we don't do anything after that. Yeah, let's just put it in the thing as well. For some reason I thought that there was even though I know that that's sometimes you just misinterpret things. Let's submit it again. Oh, wow, there's a visualize button. That's kind of cool. But I definitely have an issue here. Let's see, what does this look like? So we moved 3. I put the 2 and the 4. But why does the... So it should go to left is not none, and then it should do root is equal to node dot left. Oh. No, it has 2 chows, so it should go here, and then it set the root. Wait, what? Yeah. I will say one thing that is that when you do practice enough, you have a reasonable like errors, uncertainty of how confident you are about your code, and that's why I was saying I'm not confident about this at all. But with this 3, it should move get the 2 and then set the root to 2. Okay, I think I know for certain that that's a thing. I think I'm conflating a few things though. I think I'm missing an extra case, because basically what I did is I go all the way to the right, and then I remove that node, which is by definition a leaf, but I don't take care of the case where it's only the left and there's no right node, right? So okay, so I have to do if current.right is none, then we just set root is equal to current node is equal to node.left, node.left is equal to node.right, because there's no right is none. Wait, am I doing this right? No, root is equal to current.left. Wait, is it? No, it's just current, which is node.left. Okay, but then this node doesn't have. This is node.left.right, right? So that means this is root.right is equal to okay, I need to fix something right here. Old root right is equal to root dot right, and then root right is equal to old root right, so that we don't get rid of it. Okay, and then now we can do an else, which is this other thing. This is the most wrong answer I've gotten for these in a while, which maybe is interesting. But yeah, this should be good enough. Yeah, ace for these answers. Ooh, that's tough. That's tough. Also say that's one issue that's sometimes hard, is that like you can't really, because we have different algorithms, right? So you can't gauge from these. But clearly, you should at least have the same number of nodes. So this is wrong. Man, this is a lot of wrong answers. But you know, so I remove 3. What do I get? I guess I made a mistake in assuming that this is root. Whoops. What I should say is this should be parent. But the I don't know if this is right actually. I mean, it's kind of right, but it's I don't know if it's enough right. Let's kind of take a look real quick. Yeah, I don't think I actually well, there's just a lot of extra links. Oof, okay. So if we remove node, or we remove yeah, we want to remove node, right? Why do I do this way actually? Oh, because we want to remove the thing here. So actually we don't use the parent at all. So we have both child. We go left. Okay. We need the parent to the node, which I guess we have, so that's okay. I don't know. So then the parent to the node, and we remove the node. Okay, so if we have both child, then the node that left that right is none. Then we do this thing. We want to set. So we have a node, we go left, and that right is none. Then we want to move node that left to node. So that means that parent, if parent is none, root is equal to we do this old thing, I think, which we did. Root is equal to node dot left, and then root dot right is equal to old root right, and then basically we just have to go through this thing again. Parent dot left is equal to node, then parent dot left is equal to node dot left. Also parent dot right equal to node, parent dot right is equal to node dot left. I think now I'm getting a little bit confused because I've already at this point spent half an hour on this problem, so it's easier to be confused that way. Current is equal to node dot left. Okay, so this is still wrong because it removes an extra 4 for some reason. What is this input again? We want to remove 3, so we put the 2 here, which is fine, but then, oh yeah, okay, so we now need node dot left, parent dot left dot right is equal to node dot right. Yeah, so that looks better. Is it good enough? Let's try again. I have a lot of wrong answers for this problem already, so why not another one? Oh man. And this is just gonna be a lot more annoying to fix. Yeah, okay. I don't even know where 22. Oh, this one's 22. So I don't know. It's just a lot of pointering. And a lot of keeping track of parents and stuff. I think that's my issue here. But it's still not a. So the thing I would do with these things is try to figure out something that makes it easier to visualize, and that may be a smaller number, right? In this case, we went from here. This would be good if you don't show the data is too large to display thing, because then I at least. But I think it just takes to 21 to 22. That's what I tried to do. So I don't know why this is wrong. I mean, let's take a look at this thing. The struggle is real sometimes. I mean, everything looks okay. So what is the 20 is here? So I think I'm, for some reason. No, I mean, I think I just, this looks. I can't tell what these numbers are, so it's a little bit sad. That's the problem with these problems. But it's just, I probably just have a silly mistake somewhere, right? Is probably in this logic maybe? The problem is that I don't even know, like if I print something out, like I don't even know if that's the right answer. Parent dot left will be left. Yeah, because this node dot left has no right, right? So this is basically. Okay. Does that still give me the same answer? It should really, but oops. I feel like I'm not learning anything with this form. That's the main issue, to be honest. So yeah, it gives me the same answer. So that means it's still going to be the wrong answer. Why is this wrong? And also, I just need a visualization. I don't actually even know why this is wrong. Like, if this is okay, except for the data too large to be displayed thing, if I just remove that, then that would actually be great. Like that I could actually see like enough of it. Like the only thing that's not showing is the data is too large to be displayed thing. It seems like their algorithm just takes the larger number, the same thing except for going to the other way. So, but it seems like I don't know why that I got rid of. I think the thing that I don't understand why maybe is that I get rid of 20. So there might be some issue with that. And maybe 20 is one of these numbers. It's hard to tell because they don't show you. So I do get rid of an extra number for some reason next to 16 and 18. Where is 16 and 18? I guess it just doesn't show because it's maybe I'm just I don't know. So basically this is the input. I need a separate tree visualizer. But I could get rid of an extra cell or an extra thing. And the number I'm trying to get rid of is just 22. Right, and 22, where's 22? Here. I replaced it with 21, they replaced it with 23. It's hard to tell how to parse this. Maybe I shouldn't brag about how good I am in implementation right before that. But I just want to know what the parent of the 20 is. So yeah, maybe I'll just write something to debug it a little bit clearer. Okay, so now we can maybe figure out from this this recursive structure. Thanks for, I don't know if you're still here, but if you are, I don't know why. Thanks for kind of joining me on this, but yeah, so this is so 20 is the left of 21. Okay. So when we remove 22, somehow we just lost the left of the 20. Okay. Oh, is this right? Maybe this part is wrong. Pound is not a pound. I still have the 20 here. No, yeah, still not here. This logic is a little bit wrong. Because we want to remove node, right? So node dot right, parent dot left, remove up the left, and then is it just this? Did I mess it up? No, the parent points to the node, so we want to remove the node, right? So the parent node used to point at this and then now points at that. And then now this thing, which is the new parent dot left, that right goes to the old node dot right. Yeah. Unless I don't know. I don't think this changes though. That's why I don't know. Let's just try it for a second. Right, I am spending way too much time on this, but I thought it would be easy, but I was wrong. Alright, so the 20 is still gone, so that's not it. But where did the 21 go? I mean, we moved the... Alright, let's also print the before and after. This visualization seems to be way better than whatever the alternative, so okay. But yeah, if you enjoyed this debugging, let me know. Leave some comments. I know that this is pretty not a video that people would run into, but so 2120, and then after that 21, the left is 19. So I go left and I keep on going right. Oh. This case is trickier than I thought. So basically, maybe another visualization is something like that's a subtle mistake. I mean, it's not that subtle. I just maybe didn't think it through. But the 21 has 20 because 21 is the largest number that's more than 22. But then now we so the thing that changed is actually I was wrong. It's not in this code. It was in this code. But because of that, I removed the original node. Oh my, wow, that's a lot of edge cases. Okay, fine. In this case now, parent dot let's see, right? Now we want to replace that. So then that means that now we shift 1. So that means that this and the parent, then the parent dot right is equal to current dot left. Something like that. Let's just do well, we have to set it to I don't know, this is right. Let's see. $21.19, but is there a 20? Okay, 20 is still there. Okay, is this right though? I don't know. That's only one way to find out. I mean, maybe not. Maybe there are multiple ways, but I am a little bit tired and lazy, so let's find out this way. Okay, cool. So this was a 40-something minutes video, I think. The short answer is this is silly. I don't know. Let me think. So this is all of h time and maybe space because I did it recursively. You could do it in a way such that it's not recursive, and then it'll be constant space maybe. But what lessons can I learn from this? One is this is why I avoid these kind of tree things, and you leave things like this to the library. And there are a lot of balanced binary search trees. This isn't even balanced, but I think it's just thinking through all the different cases, and this just had so many cases. Maybe on a second pass I could clean up the code a little bit. This is about 80 lines of code. I think if I could do it again, maybe I would I don't know, have better things to handle the parents. I think that would be a little bit cleaner. But overall, just a really annoying problem, really messy problem. Let me know what you think. Again, this took 45 minutes. This is my longest problem for this month, I think. Maybe I looked at it and I was like, oh, this is going to be easy. But then clearly I was both right conceptually, but also just wrong in a lot of implementation wise. Let me know how long did you take this out this farm, and let me know. And I'll see you guys next month. Bye bye.